right, good morning. So if you are watching this, you are at home and you're going over our density activity on Monday. So when we looked at density initially, we had said that density was just a mass divided by the volume. We're looking at how tightly packed together those particles are in a given amount of space. That density, though, we can represent it in a bunch of different ways. We can look at it mathematically, we can look at the spacing of the particles, we can look at it in terms of a graphical view as well. We can look at how density is affected by mass, its volume, as well as its temperature. So when we look at density, we're just solving for mass and dividing it by volume. So in number 1, it brings back in the idea that volume is calculated by doing length times width times height, or you can always do volume by the liquid displacement that we did earlier this past week. So on number 1, you just take mass divided by volume, and you should have gotten 2 grams, and then you would be grams per centimeters cubed, because you are going to be taking centimeters times centimeters times centimeters, the length, the width, and the height. Okay. All right, on number 2, I asked for us, well, which of the cubes has a greater mass? Well, when looking at these cubes, I noticed that the length, the width, and the height, the size of the cube, the volume of the cube is all the same. So since the volume is the same, and I have different densities down here, down below, that means that the mass must be different. Because mass is in the numerator of our equation for D equals M divided by V, that means that the greater the mass, the greater the density. It's a direct relationship. So if I increase the mass, the density is also going to go up. So I just have to find the block, the cube, that has the greatest density, and that would be the one that would answer to number 2. All right, number 3 is a little bit harder because it tells you your mass of the empty graduated cylinder and then the mass of the graduated cylinder plus the liquid. So we only want the liquid. We don't want the mass of the graduated cylinder and the liquid. So if you look, the very first thing that I did is I subtracted the mass of the empty container. And then you just have to divide it by the volume. And as if you look at the very top, the volume was 100 milliliters. So my final calculation came out to be 1.05 grams per milliliter. All right, number 4, we have another situation where we are looking at a simple calculation of mass divided by volume. But the part that we want you to connect with is that density is a characteristic property, which means that if I have a substance, whether I have 10 milliliters of it or 100 milliliters of it, the density is always going to be the same. So I can always go to something like a density chart over here on the right and say, okay, well, who does this line up with? And then I know specifically the unknown material. So when you do that calculation, your final value is 4 grams per centimeter cubed. All right, now this is when it starts to get a little bit tougher because we haven't quite talked about graphing density just yet. But if you think all the way back to Algebra 1 and your pre-algebra, when you first learned about slope, you know that slope is my rise over my run, or my change in y divided by the change in x. Well, on my y-axis, you notice that my y-axis has mass, and my x-axis has volume. So if I do my rise and I divide it by my run, that gives me mass divided by volume. So the density is representative of the slope. So the steeper the slope, the greater the density. So that would be like the blue line right here. Whereas here with the red line, it has a more gradual slope. The more gradual slope you have, the less steep it is, the lower the density. Now for B, it asks for, well, what is the actual density? So the easiest way to do this would to be just see how much do I rise versus how much do I run, and just do the rise and divide it by the run. If you look super, super close, the black line is at 4, and this finishes just below it. So I estimated about 3.9, so it's an approximation. And then then I divided it by 4 because there was definitely 4 milliliters. So if you approximate it to be about 3.9, you're going to get the 0.975 grams per milliliter. All right, so on the second page, when you're going through and you're calculating, you got to be careful because look, volume is given to you first, then mass. So careful, don't take volume divided by mass. It is not going to be the same as your mass divided by your volume. So be careful. So I showed you my work for each one. I took my masses and I divided by my volume for each of these. Once I finish that, you see I have a range of range of densities from 0.45 up to 1.375. I did not round, I just kept everything as I calculated it out, but you may have rounded to the tenths place, you may have rounded to the hundredths or to the thousandths, depending upon how you rounded. Okay, so for 6, the greatest density, again, after I do my calculations, just selecting that one would be C. So then when we come down here to actually graph it, I set up my graph. Again, on the y-axis is your mass. Every other line was 1 for me. And then on the x-axis is volume. And every line on the x-axis was 1, just so that I had enough room to get up to the 24 milliliters. So if I take a look at my graphs, so I went ahead and plotted out my final volumes and my final masses, and that's kind of how I got my endpoints. And then I know that my rise over my run would be my density. So for example, A, I have it set to rise 11 and it's running 24, which makes sense because it's 11 divided by 24. So that's how I went ahead and I graphed those 4. Now looking at my lines, if I look at these, I know that the steepest one is the one that has the greatest density. So C should have the greatest density, and A is the most gradual one. It's the one that's not as steep. That would be the lowest density. So I should come back here, double check it. Does that match up? And it does. All right. Again, here is our value for mass divided by volume. If you see cc's, that just means cubic centimeters, which is just centimeters cubed. So if you're like, what is cc's? That would be cubic centimeters. It is just another way to say centimeters cubed. All right, so up here, if you look, there's water. That's the blue one. If you notice, the slope is 1. I rise 2, I run 2. Hey, 2 divided by 2 gives me a slope of 1. Hopefully you remember that our density of water is 1 gram per milliliter or 1 gram per centimeter cubed. Okay, so then that means E and F both have a steeper slope. So since they both have a steeper slope, that means that their value, their density, is going to be greater than 1. And we know that if you have a density greater than 1, you are going to sink. Whereas G and H both have a more gradual slope, which means their density is less than 1. Their slope is less than 1. And it would float in the water. So that is your question there for number 7. So E and F would sink because their density or their slopes are greater than 1. G and H would float because their density is actually less than 1. All right, 8. So it says use the graph to determine the density of the most dense and least dense substance. So again, most dense is going to be the steepest, which is E. Least dense is going to be H. So I just need to take my rise and divide it by my run. So we're going to do E together. All right, so E starts at 0 and it rises to 10 and then it runs just slightly past 4. So rise 10, run just slightly past 4. So again, I estimated mine to be 4.1. When I do that calculation, I get a slope or a density of 2.44 grams per centimeters cubed. If I do my least dense one, that would be H. I rose to about 2.5 and I ran 10. So, and you're just doing rise over run, nothing new from what you have learned in prior years from math class. So I rose 2.5 and then I ran 10. So I got an approximated value of 0.25 grams per centimeters cubed. All right, so I know the most steep one is 2.55, or I'm sorry, 2.44. All right, 2.44. And I know that my least steep is 0.25. So if I'm going to put, if I know the density is 0.4 grams per milliliter, I know it needs to go in between those. So when I draw my line, I want to draw a line that goes in between those two. Not only that, I know that the water has a slope of 1. So I know it needs to be between the water and H. I could calculate G and figure out what G's slope is, or I could just create my own rise over run that's going to give me a value of 0.4. So in order to get 0.4, I could rise 4, run 10, and that's how I ended up coming up with that prediction line right there, the pink one. Okay. So again, it is totally up to you whether you wanted to just estimate that and add it on there, because this one does ask just for a prediction. It does not necessarily have to be a perfect line. I did, because this one was a little bit easier being 0.4. I know that 4 divided by 10 is 0.4, so it was easier for me to place it on this graph. But either way, you know I would be able to place it between H and G because 0.4 would fall between those two. Okay? All right, ladies and gents, that is it. Let me know if you guys have any questions. Have a good rest of your day.